Okay, hello class. Hope you're all doing well and staying happy, healthy, and safe. Okay, so today we're going to continue our discussion of nearest neighbors approximation. But before we get into that, there's a few things that I do want to mention. One, we have a new withdrawal date for BSCS students. This probably applies to other engineering students as well, but please check with your own departments. Don't take this guy's word for it. So BSCS students, the Dean's Office has agreed that you have until the end of the semester actually to choose to withdraw from the class. So if it looks like things aren't going to go well and you'd rather withdraw from the classes, this is a possibility. But check with your local department first, even if you're a BSCS student. The next thing is a reminder of the new grading policy. Since we're in such a bizarre educational situation right now, we've added a lot of ways for you to take agency over your grades and how this affects your GPA in the end. Again, what we the professors are going to do is we're going to assign grades just like we normally do. A, B, C, D, F. At the end of the semester, when you see your grades, you can then choose to convert your letter grade into a pass-fail grade that will not affect your GPA. There are two pass options. If you make a C or greater, you can choose to go with a Z grade. The Z grade will fulfill all the requirements for your coursework, and also let this course, or whatever course you're converting for rather, count towards other classes that have it as a prerequisite. The P grade will count towards your total coursework, the credit hours that you need, but it won't count towards classes that require a C or better in a particular class as a prerequisite. And then if you get an F, it's an F no matter which option you choose, so yeah, keep that in mind. But if you're worried about the class and you don't think you're going to get a great grade in here, but you want to keep in it, just remember that you can do this option here and it won't affect your GPA. It'll only affect whether or not you can use this class as a prerequisite for another class. So if you think you can make a C or better, you're probably still going to be in fairly good shape because the ability to choose to go with the Z option. And if you don't need this as a prerequisite and you still think you're going to pass, choosing to go with the pass-fail and getting a P in here is also going to probably work pretty well for you. But keep in mind that if you do feel like you're going to fail the class, you still have this option if you're a BSCS student. If you're not, check with your department to be sure of withdrawing before the end of the semester. Okay, so moving right along. This is one way where I would ask questions of the class and give me some ideas of what kind of trouble you're having with the assignment so far. But it's not you're not here, so let's see. So this kind of reconstruction lends itself well to data that can be arranged in grids of some sort. Images. There's some examples on the course wiki where we're using this method to reconstruct missing data in images. So there's holes in an image, and you're doing different approximations, nearest neighbor approximations to fill in the gaps. But as we talked about last time, it's frequently used with map data. So you have some factor that you think varies geographically, so you sample in a bunch of different locations, and then use nearest neighbor reconstruction to fill in the gaps in between. So the K value, remember the K value specifies the number of nearest neighbors you use to reconstruct a missing value. For instance, if you choose a K value of 3, you're going to find the 3 nearest actual values that you have, say survey values for a map or something, to average together to fill in the missing values on the map you're trying to reconstruct. So the basic algorithm looks something like this. I'm going to loop through data and loop through your data and make a list of all available data values and their locations. So then you loop through all possible grid points that you're wanting to reconstruct. For your assignment in Challenge 4, it's a 192 by 120 grid. So a map of the United States for each grid point is about 13 miles across. And Uh-oh. My, ooh, what's this? Oh, I think this is a laser pointer. Is it a laser pointer? Ooh, I'm drawing. That's fun. How do I get rid of that? I don't want it. Go away. Ah! Go. Away. Okay. Let's see here. Let's do this. Ooh. Actually, kind of cool. Not exactly what I wanted to include in the lecture, however. Okay. I'm just making more pins. I grab this. Okay, so, yeah, I figured out how to get rid of those annoying little pins. Let's see. There we go. Yay! Okay, so picking up where we left off, because I really don't want to re-record this again. Okay, so you loop through your values, and then loop through, okay, so you loop through the data that you currently have, and then you loop through all possible grid points that you want to reconstruct. In this case, it's going to be 192 by 120 grid points, looking for missing values. And then loop through the list of available values once you've found the missing value, and find the ones that are closest to it to perform your reconstruction. And select those values and use them to replace the missing values. And repeat this for each grid point until there are no more missing values in the data set you're trying to reconstruct. Conceptually, this is good. This works. It seems like a reasonable approach. However, there is a problem. That problem has to do with how we typically search through data for something like this. So usually we loop through data from the top left to the bottom right. And for image data in particular, that's how it's going to be organized. That's how your data for this assignment is also going to be organized, which adds a directional bias. So if you have a set of sparse data and you're trying to reconstruct the values in between the points that you have, you end up with this directional bias because searching from top left to top right, you're always going to find those values first, which can add some unusual artifacts. So let's say that we had this data set here. We wanted to reconstruct the entire image based off of that. If we follow this algorithm to the letter, what we're going to get is something that looks like this. This is not what you're going to be looking for. What you're actually wanting to get out of this data is going to look more like this here. And as you see, these two things look very, very different. And the simple reason this is happening is for this data set, I was doing the reconstruction in the same set of data that I was pulling my neighbor values from. So what ended up happening is some of the values that we're using to reconstruct a missing value were in fact themselves reconstructed. And if you're reconstructing top down, left to right, the pixel next door is always going to be the one you just reconstructed. So you're going to end up being biased by the values that you've currently reconstructed. For this one, we're actually doing the reconstruction in a separate set of data. So this is an empty grid that we're then reconstructing in its entirety based off of the sparse grid of data that we were provided. But why did this happen? So let's look at this very simple example here. We've just got 2 points, and we're trying to reconstruct the values using nearest neighbor approximation of the empty cells just on that one line right there. So we've got 2 values provided already, our blue dot and our orange dot. And if we start moving left to right along that line, this guy is going to be the nearest neighbor of the following pixel. And then the next one, if we're going to reconstruct it, it's obviously closer to that first blue point, so that's going to be blue as well. Now here's where something interesting starts to happen. What is going to be the nearest neighbor for our reconstruction purposes of that next empty cell? It's going to be the orange one. But by strictly following our algorithm from earlier, it's going to be the blue cell because it's the one next door to it. So in this case, we're reconstructing based off of a reconstructed value. And we're going to keep finding that nearest neighbor to be the one immediately to the left until we get to our non-missing value, which was our orange one. Then after that, all the ones after it will continue to be nearest neighbors to the left, cell immediately to the left. Now what you want to do is actually maintain two grids. One is going to be your provided values, another is going to be an empty set. So your reference data and your reconstruction data. So if we do this, and we reconstruct all of the empty points over here, we only modify this one, never modifying our reference data. We end up finding appropriate nearest neighbors. So again, we get to the point where we had our tipping point earlier. So at this point, the next cell in our previous example would have selected the leftmost cell for its nearest neighbor. But this one, if we reference where it is on the reference data and where it is on the reconstruction data, we see that the next closest cell is actually going to be the orange cell. And we continue our reconstruction thusly. So if you end up with a reconstruction that's got very weird sort of horizontal streaking in it, chances are you're doing your approximation using approximated values that has that directional bias introduced by searching through your set from top to bottom, left to right. Okay, so the most straightforward way to search an image is to check each grid cell sequential search, and this isn't very efficient. So efficiently searching grid data is actually not a terribly simplistic thing to do. It's something we're not necessarily going to go over in here, so I expect you to probably use sequential search. If you want to use a different kind of search method, you're more than welcome to do that. Yeah, we're only going to go over sequential search in here, but you're welcome to use any method you want for your assignment. Again, remember we focus on function in here as long as you get the assignment working. If you use the simplest method versus the most complicated method, you still got it working. Okay. Yeah, so generally speaking, the farther away, the farther removed the data source is from the CPU, the slower it's going to be. And this is where we need to start thinking about efficiency. The slowest part of your computer is you. So when you're doing this, you're going to be checking a lot of points over and over and over. I know a lot of you like to use print statements to debug things. Well, it turns out print statements are incredibly inefficient. It takes a long time to execute them. So it's the machine, the computer, communicating data to you, and you are the slowest part of this whole system. So try to minimize the use of these statements, in particular when you're submitting your final products, that you get the whole thing executing fairly quickly. And there are really two super slow parts of this assignment. One, output, print statements that you're probably going to be using for debugging, and then the other one is doing calculations. So for this assignment, you're going to be calculating the distance from a point to another point over and over and over and over again. So you want to make sure that operation is as efficient as possible. So this is your typical distance formula. You've seen it everywhere. This is not new information for the vast majority of you. Now, this is a fairly simple equation. It's not terribly difficult. So how many different ways could there possibly be to implement it? Well, this is Python. So naturally, there's going to be 1,000 different ways to do this one simple operation. Not all of them, even though they will result in the same output, not all of these methods are equal in how much time it takes for them to execute. In class, normally we would start to taking bets right now, so to speak, on what method would be more efficient than another. But here, we're just going to talk about it sort of in a superficial way. So there's a couple different methods that we would normally talk about using the distance function as computed with a standard math library, using NumPy, using NumPy's linear algebra functions, and using the distance function built into Matplotlib. So if you're going to time a line of code, there are some things that you need to do. Import the time module, so import time. And time returns a value in seconds from the Unix epoch, which is midnight, January 1st of 1970. Now, it's going to give, even though it's giving you in seconds, it's giving it to you in fractional seconds. So you can actually get some really, really fine time resolution by using the time function here. So what you'd want to do to find out how long a single line of code takes to execute is to get the time immediately before that line, and get the time immediately after that line executes. And that'll give you the elapsed time. So the methods that we typically look at are these guys. And I'm just going to go ahead and spoil the surprise here. They're not all the same. Some of these execute in half the time of the others, even though hypothetically they're all doing the same thing. In the end, usually, now granted, test this on your individual machines. Usually, the standard math functions end up giving you the best overall performance. Usually by like quite a bit. On some machines, however, especially if you're using an older version of Matplotlib, I recently found out this is now deprecated in newer versions of Matplotlib, but Matplotlib's distance function was actually very, very efficient when I was using my MacBook with Mac ports. But, you know, using the MacBook with Python compiled from Homebrew, I got a different one of these being more efficient. And on my Windows machine, I very consistently have this one resulting in the best execution time. So since you're going to perform this calculation over and over and over again, you want to make sure that it's going to be as efficient as possible. So doing a little bit of analysis before you get started, checking to see which one of these is going to execute in the quickest amount of time for your particular machine is going to be worthwhile. Now, I included some example code at the end of the slide here. This will be posted to Blackboard, so you can just straight up get this. I'll try to copy it off of the YouTube video. So check out the course wiki. There's a discussion of getting the execution time of a single line of code there. There are other ways to do it. Frankly, there are other more Python-y ways to do it. But the method that we talked about here is very similar to how you would do it in any language in general. So this is a good thing to study up on. But again, check the course wiki. There's going to be some good information there for you. And if you have any questions about this stuff, let me know. And Deep, the class TA, is also going to be available. He can talk with you via Skype or email or however. And similarly, I'm available by Skype and email. The IEEE VR conference ended yesterday, so I'm now completely free to Skype with you guys. I'll start emailing out some Skype call links with some office hours. You just click on it and chat with me if you need to. I'm also going to be holding a Hubs get-together, so to speak. If you happen to be a student in here who has a VR headset and want to chat about this or whatnot, or do an X number of questions before you leave session. Just joking, you can leave anytime. You just log out. You can't log out of class, but you can log out of this anytime you want. I'm going to be holding a hub session, just for kicks and grins, so to speak. It's nothing required for the class. But since about 22-ish% of this class seems to have VR headsets, I figured it might be a kind of fun event to do. Hubs.mozilla.com. I think is what it is. I'll send out a link. But I'm also looking at the survey results about the live coding event. Most of you very much in favor of it. Some of you like, I don't need that. I'm good with the slides. I'm good with the video. So it's not a synchronous event. You don't have to necessarily be here to do it. If you want to ask me questions while I'm coding or ask for specific examples, this might be a good opportunity. Otherwise, I'm going to record it, I'm going to post it on YouTube, so yeah, you should be good to go. So anyway, I hope you folks are doing well, and I will see you, I guess, in cyberspace, maybe. I don't know. Take care, stay happy, stay healthy, stay safe, and wash your hands. Later.